So I start from this fancy quote, which is taken from one of the papers that Alain has just mentioned. So creating noise from data is easy. We just have to run an ergodic Markov process. Well, creating data from noise is generative modeling. So it's not that easy, but doable, which essentially for us, it will mean approximating the time reversal of the noise in the process. So now we are in continuous time. So let's create noise from data. Star is our data distribution. And one of the simplest ways to create noise from data is to use a stochastic differential equation, whose solution is fully explicit and it's very ergodic. So the supernatural candidate is Orstein-Uhlenbeck. So our forward process, noisy process, is the Orstein-Uhlenbeck process. We just have a linear drift with mean reversion. Then so it's a linear stochastic differential equation. Very simple. That and the transition density is known in closed loop. So with this we create noise from data. Let me introduce just a couple of bits, 2 bits of notation. So I will always denote by omega as it's classical the path space, so the space of continuous path from 0 up to t into RD. I fix capital T as a time horizon, is the time horizon over which I will run my model. I find P forward as below on path space induced by my forward process, and I define little P forward P, just the marginal distribution of the forward process at times T. Just to fix basic notation. So this is just the notation about the process. Let me just introduce a little bit of notation about the ergodic behavior of the process. So as it is very well known, the invariant distribution for Orstein-Uhlenbeck is just a standard function. So here, proportional to exponential minus . So this is the invariant measure, meaning that as time grows large, the forward law will converge to the Gaussian distribution, and you can quantify this convergence in millions of different ways. In particular, one result I want to recall right now for later use, you can quantify the convergence in Kullback-Leibler divergence. This is going to be very useful later on. What does it mean? It means that if you compute the Kullback-Leibler, of the law of the forward process at time t, which I denote by h, because I denote it by h because I come more from probability, not from statistics. So for me, this is relative n. Okay, but I'll try to stick with the name Kullback-Leibler because I know it's a better name. So the Kullback-Leibler divergence of pt against gamma is less or equal than e to the minus 2t times the Kullback-Leibler divergence of the data distribution against gamma. Okay, this is just one way of saying that our noising process does the job and does it exponentially fast. And for those of you who like these kind of things, of course, I'm a bit biased because I really do. So this thing here is the logarithmic subpopulation inequality for the Gaussian distribution. We don't need to go into the details about this. Just keep in mind that we have this way of checking that the exponential, that the Orff-Penrose converges exponentially faster than current distribution, and this way, and this estimate is in fact equivalent to a well-known function inequality, which is the logarithmic. Okay. I don't want to say more about this. Okay, so now we have learned how to noise. Now we have to learn how to denoise. Are there questions at this stage? Feel free to interrupt me at any time. I really don't have a fixed schedule. I just wanted to make it as accessible as possible and hopefully as clear as possible. Should I keep the fancy board? Yes, let me keep it for a couple more records. Then I will have it. Now we have to create data from noise, and as Alain has already said, we have to consider the backward process, so the time reversal of the forward process. So I'm gonna define really a definition. The backward process at time t is the forward at time t minus t. So this is of course very easy. I just define it. The thing which is trickier is what is the dynamics of the backward process? Can I write a stochastic differential equation for the time reversal of Orff-Penrose? So Alain has motivated the formula that I'm gonna write in a second with some clever approximation about the distribution of Markov chains. But in fact, probabilists have been looking at time reversal for a long, long time. At least since the 60s, and they know how to write the generator of the time reversal of a diffusion process. And in the case of the Orff-Penrose, it's going to look exactly like this. So, as you can imagine, when you do time reversal, say of a deterministic dynamics, the velocity should change the sign. So the minus xt that I had in the forward is going to become a plus. And this is very natural, but in a while I'm going to tell you that I don't like it. So I will change it in a minus, but let's keep a plus. And then there is, so here now we see the fact that we are inverting a stochastic dynamics and not a deterministic dynamics. So there is another term that comes in the truth. And this other term is, surprise, surprise, 2 times the gradient of the logarithm of the forward density t times, sorry, t minus p, because I'm taking the time. And then I have my Brownian motion, which I'm going to write here. And the thing I know is that my backward process at time capital T is low the data distribution. So this is an old.
You're missing dt.
dt. I'm missing the dt. Yes. But this is an old formula that has been known for a long time. And you see that this formula is exactly continuous time analogous of what Alain has introduced in the former lecture. And in fact, this quantity here is what people call the score. This is the score associated to the diffusion. Okay. So what score-based diffusion models try to do, they essentially try to simulate this process starting from the Gaussian distribution. And what we will try to do, or at least what I would like to do in this course, is to quantify all the errors that we make when we actually introduce the time discretization. All right. Are there questions at this stage? Maybe. Okay, maybe now what I will do now, I will tell you why I don't like the plus. And
this is backwards suggesting.
No, this is,
Final issue.
no, but actually, if this is perturbing for you, just don't look at this. All I'm saying is, okay, let me do it like this. Of course, it's not super brilliant, but this is really a forward differential equation. So differentiation. What I should maybe what I should precise is that this granular motion, of course, has nothing to do with the forward direction. What I mean is that in low, the backward process satisfies this, but there is no relation between the products. No relation whatsoever. Okay, there will be backward stochastic differential equations. All right, now the next thing I'm gonna do, as I said, I'm gonna try to convince you that having a plus here is a bit annoying, and what can we do to change to put a remedy to this? So why is it a bit annoying? Because suppose I don't have this part here. So recall that the Ornstein-Uhlenbeck was a very ergodic process, so it goes exponentially fast to equilibrium. Now I change the time around, and instead of a minus, I get a plus. So it seems that the backward is nothing, so it's really not ergodic at all. But if you think about it, if you start Ornstein-Uhlenbeck in the invariant measure, it's well known that this is a reversible process. So flipping the time around should not change the dynamics. So you don't see this very well from this one. Okay. So what you can do is to introduce the relative score. So you introduce the score relative to the Gaussian distribution. And by doing this, you will restore the right sign here. And then you're happier because even the backward is somehow ergodic. And of course, you're going to need these estimates when you analyze the performances of the of score-based diffusion algorithms.
So why is the score called score?
Actually, this is the part where I will use my jolly. I'm not really a statistician, so Alain will know it for sure.
It's a gradient of scores.
Yes. But let's change it. Let's change a little bit. So I'm going to introduce the relative score. Following vector field. So instead of taking just the forward, I just take the radon-nickel density of the forward against the Gaussian distribution and evaluate. This is the relative score. So with this notation at hand, you can see that the backward process is exactly dynamics that I wanted to have. So here I get my minus, so I'm happy because I have ergodicity. And then here. Where there is nothing particularly brilliant here. It's just that the logarithm of a Gaussian is a quadratic function, so take the gradient of the linear function. So nothing. But this is going to be quite useful. This viewpoint is going to be quite useful later. Okay, so then the next thing I would like to discuss a little bit about is this representation of the score in terms of a conditional expectation, which is exactly what makes the computation of a score relatively accessible in practice. So I'm going to kind of go again through what Alain has discussed already, taking a bit advantage of the fact that we're in continuous time, so gradients are a bit easier to compute, and variations of functions are a bit easier to compute. And of course, if you have questions about working the time, please ask. I didn't explain how you get this formula, but tomorrow I will actually give kind of a proof of why this is. Okay, now I can erase the quote. Also, maybe another comment before I begin, I'm going to represent this score as a conditional expectation, not the relative score. But of course, they differ by a linear function, so there's no problem. You can represent one. Okay. So, all right. Let's introduce another bit of notation. I'm going to need the forward density, forward transition density of the Orstanulin group. Is kind of the analogous of the transition density of the Markov chain that Alain has discussed in the previous lecture. So, very well known, the transition density of the Orstanulin semigroup. Well, it's a Gaussian, so we put proportional. This means proportional to up to a multiplicative constant, and anyway will disappear when I take the gradient of the log. Plus this is E minus Y minus a certain parameter mu P x power 2 over 4t, because I put the square root of 2. Sorry, for not t, but no, let me just put 2 times sigma t, where sigma t is the variance of the extended process. These parameters are fully are known explicitly, so mu t is e to the minus t, so the Orstanulin tends to forget the initial position exponentially fast, and sigma t, if I'm not wrong, is 1 minus e. So you see that the variance stabilizes to 1 exponentially fast again when time goes to infinity.
For a statistician, this is not very nice because the variance is sigma, not sigma squared.
Yes. Okay. Okay. No, indeed, I agree. I think it's a better choice. All right.
You had, I think, 4 before.
Yes, because no. Okay, this is because there's always it's endless debate. Now it's a probability versus analysis. Should I put Brownian motion on square root of 2 Brownian motion so that I get Laplacian, not 1/2 Laplacian in the PD? So I had put the square root of 2. So I was thinking I should put a 4, but that's because I was not taking into account that we have Orstanulin, not just the cluster. Anyway, up to division and multiplication by 2, everything here is correct. But so just to say, the actual expression does not really matter. That's the important thing is that you know how to compute them. They're fully explicit, and they stabilize exponentially fast. We don't care about them. All right. And well, with this nice notation at hand, of course, we have immediately expression for the forward transition density. Just integral of the the forward marginal density, the integral of this transition density against the data distribution. Okay. Of course, now I can take the gradient, expect y. And by doing some simple calculation, of course, out here I will always neglect the fact that I should justify why I bring the gradient inside, but it's really not the problem we're facing now. Immediately get this. What did I do? I brought the gradient inside, then I divide and multiply by the transition density. So here I get the gradient of the log, and here I get the joint density at time 0t. Okay. So feel free to ask any questions. And now I'm gonna use the color chalks. Because now I'm gonna divide by dt right here. So that this object here is now the gradient of the log of the forward. So this is actually my score. And I have to divide by y here. Now what you're going to realize that, that this thing here, so if I'm taking joint density divided by marginal density, this is the conditional density of the position of the process at time 0, knowing the position of time. So, in more probabilistic notation, this actually means, I'm trying to write here, that my score coincides with the conditional expectation of. So the nice thing here is that this is once again, I'm computing the gradient of a quadratic function. So this I know explicitly what it is. So this is minus sigma squared e to minus 1. No, actually, I will use the fact with profit from my new notation. And then this will be x forward e minus t. Well, let's put here t of x 0 conditionally on I'm sorry, but somehow I have. Is it clear? It's okay. Should I shift a bit more to the right? Centimeters. Okay. maybe since this is kind of.
No, but I think this is okay.
It's okay. So I'm sorry for the.
You're just cutting the bracket, the right bracket. Okay. But not if you put it full screen. Okay.
All right. But somehow, okay, this is like what creates a bit the excitement about our score. We can compute it. And maybe Alain has already said how you do it in practice. So you use the fact that conditional expectations are L2 projections. So you write the this vector field here in terms of a minimization problem. And then you minimize an empirical version of the loss function by taking IID samples and using a stochastic gradient descent. I don't know if I should go through this again. Maybe no, but if you want, there's no problem. I can start. But maybe I would like to make another comment, and maybe many of the comments I will make are the comments of somebody like me who is more a mathematical background, and sometimes is a bit puzzled by what statisticians say. Oh, it's easy, or it's interesting, or it's hard, or so. So here you really see the advantage of using a noising process that is the simplest possible. Because you could think in principle that, okay, I have my data and I have some physical intuition about the data. So I will noise them with a process that somehow translates this physical intuition into a stochastic dynamics. Suppose your data come, I don't know, from earthquakes, that you should simulate a dynamics that kind of resembles the dynamics of an earthquake. But what's the price to pay is that the diffusions for which we are able to compute the gradient of the heat kernel are essentially only Gaussian diffusion. Otherwise, this would have a very complicated expression. So here you see why it is useful in this setting to have the simplest forward dynamics you can, because anyway, the backward is going to be complicated. All right. Yeah, if
But indeed, if you have a very bad new star, for example, which is not very one, this formula would help.
so if okay, new star, you mean that does not have a first moment?
Yeah.
Yeah, okay. I guess in practice you always start from samples, and empirical distributions always have first moments. I would say maybe Alain is better inside that admitting a first moment is rather mild assumption. From my perspective, like of somebody who tries to show guarantees
You
of
mentioned earthquakes. It's a setting in which maybe
why did I do that? Okay. I should have stick with the cat. Okay. Cat power.
And what?
But okay, of course, maybe. Thanks for the question. Of course, the regularity I have on the data distribution is going to be like one of the main factors entering the analysis, convergence analysis. So how does the model run in practice now? So let me just give you some a version of the implementation. Yeah, I think I will take it right quite large. So. So let's write down more or less how the algorithm looks like. Okay, so essentially, what we need to have is something that approximates the score in a time discretization. Okay, so I need a partition of my time interval. Okay. And I need, so I've run my neural network, so I obtain score approximations at all points of the partition of the time. So what I have are vector fields, which are denoted by S star pk. They're vector fields. That approximate the score. What does it mean? It means that more or less, star k as a vector field is similar to the score at time tk. So how do I compute them? Once again, with the procedure that Alain has discussed. I will not discuss the implementation of that procedure already because Alain has given some insight, and also because that's not somehow the new part of this course. You just have some approximation that you compute with your. And then how does the model work? So let me maybe wait, fix it here. I think it. So it's essentially an Euler scheme on the time reversal, where you replace the part where you have the scores with the estimate. Actually, maybe to simplify life a little bit, I will take approximations of the relatives. But I like this better and less. So X star is going to be my model, my generative model. At time 0, I initialize with the Gaussian because I want to create data from that. Right? And then on each sub interval of the partition, I'm gonna run an Euler discretization of the time reversal with a little maybe spread. So my part. This is true for E that belongs. So this is not completely an Euler scheme because you see I'm doing really an Euler scheme where I replace the actual score with my approximation in this part. But here I'm fully integrating this part. I'm not approximating this. I'm not writing X star of TK, but this is just because this part is linear, so it's easy to have a solver that can somehow take care of this part exactly. Okay. I mean, I
like a splitting scheme.
Yeah. Splitting scheme. Okay. I believe. Okay. So just to say, this is not at all the harmful part in the discretization. This is the part where you need to work. Okay. All right. So at the end of the day, as we said, it boils down to some Euler scheme. So let us now maybe try to make a list of all the errors that we make with respect to just taking the real-time reversal. So maybe let's try to do this. Let's try to do this kind of together. So what errors do I make while doing this? So there is a first one, which is here. I'm initializing at the Gaussian. The time reversal does not start from the Gaussian. It starts from the law of the forward at time capital T. So the first error I make is initialization. Because of course, gamma very different from the law of the forward. No, not very. Gamma is different. But here we see already why did we choose Orstein-Uhlenbeck? Because Orstein-Uhlenbeck is gonna make these two exponentially close in capital T. So this error will be mitigated when capital T is large. So this error doesn't look too dangerous to handle. Then of course there is another error. Well, yeah, score approximation. Not using the actual vector field that I should use, I'm using some thought. But here, since we are mathematicians, we will put the right hypothesis so that this doesn't become too bad. No, I'm kidding. Here, you can. So as Alain said, you have reasonable statistical procedures that allow you to control this error quite well. Then there is a third error, which is the time discretization. Of solving exactly an agreed outcome. And this is the bad guy. This is the one that's difficult. I'd like to try to give you an idea on why this is the one that's complicated. Because after all, I said already a few times, this is an Euler scheme. So you can just Google and find huge body of literature about the convergence of Euler schemes for stochastic differential equation. But typically, if you want to make an Euler scheme converge, you need hypothesis on the coefficients of the limiting SD. So typically, you have something like if the diffusion matrix is Lipschitz, if the drift is Lipschitz, or one side is Lipschitz, or if its derivatives are not too big, then you can make the Euler scheme converge. So actually, you could say, okay, I want to do the same here. So I'm just going to estimate the derivatives of the score, and then I just take my favorite Euler scheme paper and I apply the result. This is actually what the first papers about convergence guarantees for this model did. It's very reasonable, but there is one problem. Because actually, if you really want to have estimates on the derivatives of this of the score, you have to impose strong assumptions on the data distribution. And the way to guess why this is the case is that for those of you who know a bit stochastic control or control, I will come to this tomorrow. This object here is actually the gradient of a Hamilton-Jacobi-Bellman equation. And it is very well known that if you want two-sided bounds for, say, the Hessian of Hamilton-Jacobi-Bellman, this is really hard. It is really hard. So that's why somehow the strategy of establishing some regularity on the score, then applying classical analysis of Euler methods, it's not maybe the best. So what I'm gonna try to tell you tomorrow is somehow how to use the insight that you have on the geometry of this problem in order to avoid completely the avoid completely considerations about the regularity of these vector. Okay. But again, some analysis is possible with this approach. To repeat maybe what Alain said, they are old paper. By old means 2022, but somehow the production is just skyrocketing. So old papers, 1.5 years ago, they were doing exactly this. So as I said, somehow this source of error is kind of okay. This is what I say, also kind of okay. And this one is the bad guy. We'll see tomorrow. Maybe. How to run. Okay. All right. So this is the algorithm in a continuous time that kind of corresponds exactly to what Alain has introduced. Okay, to continue with this line of silly jokes, this is an old algorithm because there are new ones that have just come out some months ago. that I'm not even in the position to say whether they're better or not than this one, but there are algorithms that exploit similar ideas and do and create other ways to interpolate between probability distributions. So I will stop here for today about the classical score-based diffusion models. This is the generative model that you consider. Tomorrow, hopefully, I'll give you some details about the analysis of this model. And now I'm going to make a small incursion on the, so to say, probably newest algorithms that have come out recently. I will put some references in my lecture notes. And again, I will not be able to present you a complete overview of these algorithms because there are really many. But I will present you one that is gaining quite some popularity and that somehow echoes a bit this construction, which is diffusion flow matching. So are there questions about this? If not, I'll move on to diffusion flow matching. So the analysis of this is gonna come tomorrow. And the reason also why I think it's a nice idea to introduce these new algorithms is because they will allow me to connect with something else that I'm much more familiar with. So this new algorithm actually will kind of make a bridge. A bridge is a bad choice of word. Will kind of connect this with optimal transport and entropic optimal transport. So I will try to sketch this in the remaining time of this thing. Okay, so we move on to actually diffusion flow matching. Then I will present at the end even a more newer version. So to introduce this algorithm, let's take a step back. So far, somehow, most of the propaganda has been about, wow, these generative score-based are super nice. But maybe there are some things that they don't do that well, or that you would like to do differently. So score-based diffusion models, as the one I presented, they interpolate between noise and data. So at least one of the two distributions has to be simple. It's noise. Sometimes, so suppose you want to transform cats in dogs, you may want to interpolate between distributions that are arbitrary, they are given. So you don't want to generate a cat from noise, you want to generate a cat from a dog. This is more or less the way I would put it. So sometimes you want to interpolate between arbitrary distributions. Another thing about score-based diffusion models is that, yes, they create noise from data with the forward, but it takes them an infinite amount of time. As I said before, when you actually implement the algorithm, you fix a time horizon, you start from the Gaussian, so you introduce an initialization error, and in order to mitigate the error, you have to make the time large, the time horizon large, because you want to use the ergodicity of Einstein. So sometimes you just have a fixed time window. You can't allow t to be very large. So you may want to do interpolation over fixed. Right. I will always choose 0. So score-based diffusion models, they do none of the two. And recently, a new class of algorithms has been proposed. So diffusion flow matching is just one instance of one version of these algorithms, which are called stochastic interpolants. So the base name is so I would say the basic idea behind these algorithms, let's say behind diffusion flow matching, is the following. Suppose you have to interpolate between a Dirac in X and Dirac in Y, and you are a probabilist or well, whatever, but you know Brownian motion. The first thing that comes to your mind is, okay, I draw a Brownian bridge. Starts from X and ends in Y. Okay, if I have point X here, point Y there, I can draw a Brownian bridge or simulate. Well, I draw it, but you can simulate it. That goes from X to Y time. And we know everything about Brownian. And then if you don't have Dirac, but you have real measures, well, you just mix bridges together. So if I will give you a more mathematical definition of what does it mean to mix bridges together. But if you're a bit familiar with optimal transport, this is not so strange. In classical Moore-Kantorovich optimal transport, what do? You compute the Morse map between one distribution and the other. So you know that point X has to go to the point T of X, where T is the Morse map. And then how do you construct what people call the geodesic of optimal transport? You draw lines. So you know that you start in X. You know that you have arrived at T of X. At time T, you just walk along the line from X and T of X at constant speed. This is exactly optimal transport. Here is what is a constant speed stochastic process that goes from one point to the other. Well, this is the simplest choice, is the Brownian bridge. Okay. So this is just to sketch a first connection with optimal transport. Now let me be a bit more rigorous. Let me just talk a little bit about Brownian bridges. So recall that I denoted by omega the space of continuous trajectories. Now I fix my time horizon equal to 1, and now we call R. R stands for, so maybe I took reference measure. This is the law of a Brownian motion. So it's the Wiener measure. And here I do something that may sound a bit strange. It has sense in statistical mechanics, but you can think about the Brownian motion started at your favorite distribution. But for calculation purposes, I will take the Brownian motion started at the Lebesgue measure, which doesn't make sense. It's not a probability measure, it's just a positive measure. So probabilistically, it's a bit odd, but it's reversible in time. That's a big advantage. But okay, you can just think. So that R is I write the reversible Brownian motion. But if you, maybe I'm making I'm making it a bit too complicated. Just you don't like this word, just ignore R is in Brownian motion started with a Gaussian distribution. Reversible means I start from the Lebesgue. So it's a law on path space. It's the Wiener distribution. And then I want to build my bridge. So x and y, find the bridge simply by conditioning the Brownian motion to start at x and stop at y. So I write omega, little omega for the canonical process of 0, 1. So this is just Brownian motion. Conditionally on, I start from x and I end up. So this is the measure, the distribution of the Brownian bridge. It's just defined like this. But of course, this is not so user-friendly because in practice, how do you construct this? Luckily enough, there are many more or less explicit representations of the Brownian bridge. I'm going to give you one. It's not the only one. And in fact, people who work with stochastic interpolants often choose other representations. So you can write down a stochastic differential equation. Whose law will coincide exactly with the law of the Brownian bridge. So if you consider this one, you see I have a drift that has a sort of tendency to drag me towards the final point, and this tendency becomes larger and larger when the time horizon, when the time goes to 1. So of course there will be some singularity at the end, because I really have to end in fixed form. Square root of 2. If I take this stochastic differential equation, where B is some given Brownian motion, then the message is, you can, I will not prove this, but the bottom line is that if you take the low but phase of your solution of the P, this is actually equal to the Brownian bridge. Okay. Okay. That's a little introduction of Brownian bridge. Okay. And just maybe small comment. You see that here there is a bit of time reversal flavor, because if you look at this, this is the gradient of the log of the heat curve. So let's start. Now we have bridges to connect points, and we want to connect measures. So we will need just one more ingredient, and then we have a nice way to bridge between measures. So how my stochastic interpolant is going to look like? I have two measures, mu and nu, that are given, and I want to interpolate. So I take any coupling of the two. I'm going to define what a coupling is. I sample initial and final position according to the coupling, and then I draw the bridge in between. Okay. So let me introduce a set of couplings. Mu and nu are two probability measures based on B, and the set of couplings of mu and nu. Now I have already introduced this, but as a refresher, the probability measure on product space such that The first marginal is mu, sorry, and the second marginal is mu. I write it like this. This is true for all A's, which is, well, a Borel set. Did I say something?
Sorry, I don't. I mean, the sign in the previous equation. I mean, this 5 minus 16.
Because here you would like a plus.
But the fact is that if x is larger than y, you expect the derivative to be negative, no? Because it goes towards y, or not?
Yes, if x is larger than y, you expect there. Yeah, sorry, I flipped it. Yes, because of yes. Yes, there was a tiny problem. You want the bridge to bring you down to y if you're up, and up to y if you're. There is a problem with this. Thanks. Actually, maybe two. Okay, two. Make one more comment. The Brownian bridge should be some sort of very degenerate Holstein-Uhlenbeck. That is, what mean reversion is so strong that brings you to the final position. And so it's actually a time-dependent Holstein-Uhlenbeck. Want an Holstein-Uhlenbeck to have mean reversion, you need a minus in front of the x and not the plus that would have been the result of two minuses. Okay, I have coupling, I have bridges, and now I can define my stochastic. That goes exactly as I said in words. Construct it in two steps. So the input is a coupling of mu and u and bridges. So the first thing you do, you sample initial and final position according to your coupling, favorite coupling. And u, and of course, the obvious choice is to take the independent coupling because it's the easiest to generate. But of course, this had its problems. I will try to address them. And then simply you define your process xi t, or t in 0, 1, as the Brownian bridge between x0 and x1. Right. Where, of course, I am assuming here implicitly that this random vector is independent from the b that drives the stochastic differential equation that I wrote. Okay. So this guy, how we call stochastic. First, you see immediately that this stochastic process has the right margin by just by the way I constructed it. Time 0 has low mu, and time 1 has low mu. It has other properties. I just want to give a more measured theoretical version of this definition. So here you see that there is no distinction anymore between forward and backward. It's not clear a priori that one measure is more important than the other. So I will not use arrows. I will still define capital P of I as the law of my stochastic interpolant on And what is the theoretical version of this? If I want to compute pi of a certain set A, like this. Well, I'm just integrating the probability that the Brownian bridge falls into A. A is just some measurable set of continuous paths. And I integrate against the coupling that I've chosen. The measure of just probability. You don't want to look at the process. Okay. Half an hour. Okay. All right. So let's have a look a bit at the properties of this guy. So somehow something suspicious. So if it's so simple, why did you bother with generative modeling, score-based? So one interesting property is that pi, so the interpolant, has the same bridges as the Brownian motion. What does it mean? Is that if I condition pi on its initial and terminal value, I find a Brownian bridge. This is essentially implicit in the definition. Maybe what do I mean by this? If I here, of course, it would be for x, I, y in the support of the coupling, but that's not important at this stage. So this is the bridge of pi. Should I define it? It's really the same thing. I take the law of pi on path space and I condition on initial position equal to x, final position equal to y. This is the bridge defined for any law on path space. So actually, processes with this property have a name. This actually means that pi belongs to the reciprocal class of the Brownian motion. So actually here it starts quite a funny story. So reciprocal processes were introduced like in the 30s to explain some quantum physics. I will not be able to tell you how, but somehow they were studied almost a century before these stochastic interpolants. So much older than 2022. So otherwise said that pi belongs to the reciprocal class of the Brownian motion, which I denote by calligraphic R. What is the reciprocal class? That the set of probability measures whose bridges coincide with Brownian bridges. Otherwise said is the set of P path space such that essentially you have this decomposition here, where instead of pi, you just have the marginal low at time 0, 1 of your distribution. This is the integral of R y a 0, 1 dx dy, where t0, 1 dx dy is the margin of, so the joint margin. So it's the probability that omega 0 is on x, omega 1. Okay. Then this is somehow interesting because it tells us that the bridges of my stochastic interpolant are Brownian bridges, which are marked processes. So the conditional laws of my process are Markov. The funny question is the process itself Markov? And the answer is no. In general, you cannot represent this guy with a stochastic differential equation as I wrote it before.
So what you're saying is that if you take like two Dirac delta measures on one side and the other, then this is
yes. But
but
when you reintegrate with respect to the initial and final distribution, what you get is non-Markov. The basic, just to give you the basic intuition for this, is that for a diffusion, if it was a diffusion, it means that the initial distribution and the driving noise are independent. But here, the thing is that what you prescribe is the full load at time 0, 1. So there is no reason why this should be. So
like a dependent mixture of Brownian bridges.
Exactly. It can be any mixture of Brownian. In particular, if you take the independent coupling, it's never. Actually, if you like a stochastic equation with delay, you could represent it as you could represent the law as a stochastic differential equation where the drift depends on initial position and on the current position. But of course, this is not Markov. And for quite some reasons in machine learning, you would like to have a Markov process. First of all, because you want to have flows, you want to have velocity fields, so you need to have a Markov. But there is also another reason why you somehow would like to change your process a little bit. It's because, as I said, the coupling pi, you tend to choose the easiest possible because you want to construct something that interpolates easily. But if you take the independent coupling, suppose you're trying to match cats and dogs, it means basically that if you take the independent coupling, you do something which is not very smart, because it means that essentially you sample a cat, and then you sample randomly a dog, and you match them. Whereas, of course, what you would like to do is to assign to a given cat a dog that resembles the cat according to some criteria. Right? This is okay. So,
what is Markov again?
Markov just means that it has a Markov property.
Which object is Markov?
The bridges. So these are Markov because are Brownian bridges, which are stochastic differential equations, and they are Markov. No,
I'll ask you that.
Yeah, but of course, it was
in general, they are shiny Markov.
yes, they have this Markov field property. They are Markov fields actually. There are one-dimensional Markov fields indexed on time. So yes, as I said, the other reason is that you want to improve the coupling. So if you start with this coupling, then constructed interpolant will not change the joint distribution at time 0, 1 of your process. So you will still have a coupling that does not really reflect what you want to do with the data. So it seems that you're stuck because the process is not Markov and you want to make it Markov. And the coupling is not good. So what can you do? Actually, you can compute, and that's what these algorithms do, you can compute the so-called Markovian projection of your process. So the measure on path space is not Markov, there is nothing you can do, it will never be Markov. But if you take its marginal flow, so the collection of its marginals, you can find a Markov process with marginal flow coincides with the marginal flow of the interval. So let me write it down. So you say, okay, I define marginal flow. This is the law of the interpolant. Given time, this is, of course, it. Of course, somehow the thing which makes it possible is that knowing all the marginal is much less than knowing the path distribution. Path distribution takes into account correlation between different states at different time points, and the marginal flow just doesn't look at it. So the idea of diffusion flow matching is I take this flow and I replicate this flow with a stochastic differential equation of Markov type, standard SD. So I need to compute.
So this is just the law of the marginal of the flows.
Yes.
Why do you say it is a flow?
Just terminology that people I think comes from optimal transport. So you call, okay, typically maybe put because I will mix this maybe. So typically any curve in the space of probability measures, so just a sequence of probability measures on RD indexed by time, you can call it a flow. But it's just this is just the collection of all marginals. Okay. So let me write it. So what is the idea of diffusion flow matching? Represent the flow, marginal flow, with a Markov process. Well, let's say with a Markov. So what your algorithm will learn a brief feed that represents the marginal flow.